Good day everyone, I am Sir Roy and for today's lesson we're going to talk about the quantum mechanical model of the atom. This particular lesson will cover the most essential learning competency, which is explain how the quantum mechanical model of the atom describes the energies and positions of electrons. So let's begin. Let us first have a review of the atomic model and the theory timeline. It all begins with Democritus. He proposed that matter could not be divided into smaller pieces forever. He also claimed that matter was made of small, hard particles that he called as the atoms. The next one is Dalton. Dalton viewed atoms as tiny solid balls. He then created the very first atomic theory. He was followed by Thomson. Thomson in his model was known as the raisin bun model or also known as the raisin bread model. He showed that the atom was made of even smaller things. Next to Thomson is Rutherford. He showed that the atoms have positive particles in the centers. Rutherford also discovered the protons and the nucleus. After Rutherford, we have Bohr or Niels Bohr. He proposed that the electrons move around the nucleus in specific layers or shells. He improved on Rutherford's model. After Bohr, we have James Chadwick. Working with Rutherford, he discovered particles with no charge. This is what we called as the neutrons. And for the modern one, the new atomic model has electron moving around the nucleus in a cloud. So work done since 1920 has changed the model. For the introduction, let us look at this illustration of the solar system model. We can notice that the sun is the center of the solar system while the planets are revolving around it. It is somewhat comparable to the planetary model of the atom, wherein the nucleus is located at the center of the model while the electrons are orbiting the nucleus in its orbit. Let us discuss the Bohr model of the atom. This particular model was familiarized by Niels Bohr. He was convinced that the atom could be pictured as a small positive nucleus with electrons orbiting around it, just like the solar system. Bohr pictured the electron moving in a circular orbits. He associated these circular orbits to what we called as the energy levels. Then he suggested that the electron could jump to a different orbit by absorbing or emitting a photon or an energy of light with exactly the correct energy content. Next one is the wave mechanical model of the atom or the quantum mechanical model of the atom. This one was popularized by Louis de Broglie and Erwin Schrödinger. They suggested that because light seems to have both the wave and particle characteristic, meaning to say it behaves simultaneously as a wave and a stream of particle, the electron might also exhibit the characteristic of both these. Now, let us analyze the illustration. We have wave pattern 1, wave pattern 2, the wave axis, and the nucleus. This particular model states that electrons are almost as much like a wave of energy as they are like particles, just like the title itself, the wave mechanical model. Means to say they are moving so fast that they are not really in any one place at any given time. Means to say you cannot find the electrons at a particular location at a particular time because they are moving too fast and they keep changing their path in response to the fields around them. Now let's have here the concept of the quantum numbers. When we speak of the quantum numbers, we are referring to the value that is used when describing the energy levels available to atoms and molecules. Now we have four types of quantum numbers. These are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. Let us discuss them one by one. Let us start with the principal quantum number, which is symbolized by letter N. So it describes the size and the energy of the orbital and relative from the distance from the nucleus. The possible values of n are positive integers, so may begin with 0, 1, 2, 3, 4, and so on. Next, when the value of n is smaller, it means that it has a lower energy, and it means that it is closer to the orbital of the nucleus. We sometimes refer to the principal quantum number as designating the shell the electron is occupying. So remember, for principal quantum number, it describes the size and the energy of the orbital. Next, we have the angular momentum quantum number, which is represented by letter L. This describes the shape of the orbitals. Its value is related to the principal quantum number and has allowed value of 0 to n minus 1. For example, if n is equal to 4, then the possible numbers of L would be 0, 1, 2, and 3. Since n minus 1 or 4 minus 1 is equal to 3, let's begin with 0. So we have 0, 1, 2, and 3. So let's have this illustration. For the s, or if the value of L is 0, that would be in s orbital, and it has a shape of spherical. If the value of L is 1, it falls under the p orbital, meaning to say it has two lobes, as you can see in the illustration. If the value of L is 2, it is found in the d orbital, which has four lobes. And if the value of L is 3, it has 8 lobes, which can be found in the f orbital. So let us use this particular legend. For s orbital, s stands for sharp. For p orbital, p stands for principal. For d orbital, d stands for diffuse. And for f orbital, f stands for fundamental. Now, the third one, we have the magnetic quantum number, or represented by ml. It describes the orientation of the orbital sound around the nucleus. The possible values of ml depend upon the value of L quantum number. The allowed values for ml are negative L, though 0 to positive L. For example, for L is equal to 3, the possible values of ml would be negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. This is why, for example, if L is equals to 1, that will fall under the p orbital, right? There are 3 p orbital sublevels corresponding to ml values of negative 1, 0, and positive 1. Next one, we have the spin quantum number, the last type of quantum number, or represented by ms. It indicates the direction of the electron is spinning. There are only two possible values for ms, or the spin quantum number. It could either be positive 1/2 or negative 1/2. When two electrons are to occupy the same orbital, then one must have an ms, or spin quantum number, positive 1/2, and the other one, or the other electron, must have a spin quantum number of negative 1/2. These are what we call as the spin paired electrons. Now let us try to assign the four quantum numbers. Let us answer the following question. If n is equal to 7, what are the possible values of L? Since L can be 0 or a positive integer less than n minus 1, it can have a value of 0, 1, 2, 3, 4, 5, and 6. Remember, the formula is n minus 1, so we have 7 minus 1 equals to 6. So All the numbers below, including 6 below, can be part or possible values of L. Next one, if n is equal to 3 and L is equal to 2, then what are the possible values of ML? The answer, since ML must range from negative L to positive L, then we have ML can be negative 2, negative 1, 0, 1, and 2. Remember, if we have n minus 1, that would be 3 minus 1, that is equal to 2. And since we have a range of ML from negative 1, ay negative L to positive L, that could be negative 2, negative 1, 0, 1, and 2. Next one, we have here the electronic configuration. This was contributed by Wolfgang Pauli in cooperation with Niels Bohr. So this particular concept of assigning electrons followed two principles, and these are the Pauli exclusion principle, which states that no two electrons in an atom can have the same set of four quantum numbers. And the other principle is what we call as the Aufbau principle. Describe the order in which the electrons enter the different orbitals and sublevels. Speak of electron, it is the representation of the arrangement of electrons distributed among the orbital shells and subshells. Now, in writing the electronic configuration, we can see that we have here the numerical coefficient, which is 1. This represents the row or the subshell or the shell, and the possible numbers could either be from 1 to 7. Then we can also here see the letter, which is S. This represents the subshell. This could either be S for sharp, P for principal, D for diffuse, and F for principal. And here you can see number 1. This one represents the valence electron, which is possible for each subshell. For S, the maximum number of electrons could be 2. For p orbital, the maximum number of electrons is 6. And for d orbital, the maximum number of electrons is 10. For f orbital, the maximum number of electrons is 14. And we should follow this particular series in order to arrive with the electron configuration of an element. So let's start with 1s, of course. Then just follow the line, followed by 2s. Then we have 2p, 3s. Then we have 3p. Then 4s. After 4s, we have here 3d. Then we have 4p. Then followed by 5s. Then we have here 4d, 5p, 6s, 4f, 5d. We have 6p, 7s, 5f, 6d, 7d, 7p, up to 8s. This is what we call as the electron configuration pattern. Now, let us have an example. The given element is boron, which is an atomic number of 5, meaning to say the number of electrons is also 5. So by looking at the pattern, the electronic configuration for this particular element would be 1s2, 2s2, then 2p1. Try to look at this exponent. We can see that we have here 2 plus 2 equals 4 plus 1 equals 5, right? So this one is equivalent to our number of electrons. As we can see, 1s1 is here. Okay, the maximum number of electron for S is 2. So we have already 2 electrons. Then we have still missing of 3. So followed by 2s2. So we have to put 2s2. So we already have 2 plus 2, 4 electrons. Now, there is one missing electron that would be fall under 2p. The maximum number for p orbital is 6. But then again, we only need 1. So we write only 1 here so that we can satisfy the number of electrons, which is equal to 5. 2 plus 2 equals 4 plus 1 equals 5. So let's stop with 2p1. Therefore, the electronic configuration of boron is 1s2, 2s2, and 2p1. Now, let's have the box diagram. It is represented by boxes grouped by sublevel with small arrows indicating the electrons. The s orbital is represented as one box with maximum of 2 electrons. For p orbital, there are 3 boxes, maximum of 6 electrons. For d orbital, 5 boxes with maximum of 10 electrons. And for f orbital, we have 7 boxes with maximum of 14 electrons. Let us have this example. Again, boron, which is an electron number of 5. It has electronic configuration of 1s2, 2s2, and 2p1. How about the box diagram? So as you can see, let us first uh, break down the electronic configuration. We have 1s, 2s, and 2p. Again, s orbital is represented by one box. And 2s also represented by one box. And we have here 2p. Since it falls under the p orbital, it is represented by 3 boxes. So here, let us first put the upward arrow. Okay? So you have to fill in first the upward arrow before you fill up the downward arrow. So we have here 1, 2, and 3, followed by 4 and 5. So there are 2 upward arrows and 2 downward arrows. So this is the box diagram for boron element. Next, let us try to get the electronic configuration of the following element. Let us first start with sodium. Since sodium has atomic number of 11, therefore it has a number of 11 number of electrons. So we have here the answer of 1s2, 2s2, 2p6, and 3s1. Again, how do we get that? So let us first start with 1s1, 1s. The maximum number of electrons for s is 2. Okay? So we still have, so 11 minus 2, we still need 9. So again, followed by 2s2. The maximum number of electrons for s is again 2. So we have 2 plus 2, we have 4. 11 minus 4, we have 7. So still we are missing with 7, followed by 2p. So we have the maximum number for the maximum number of electron for p orbital is 6. So we can write 6. So 6 plus 2, we have 10. Still, we need 1. So we have to include 3s. Since we only need 1, instead of writing 2, since the maximum number of electrons for s is 2, we need to write only 1 here so that we can satisfy the total number of electrons, which is 11. So we have 2 plus 2, 4 plus 6 equals 10, and plus 1, we have here 11. Okay? Next, how about for oxygen? All right. So we have again for 1s2, 2s2, and 2p4. Just follow the given sequence. So in order to check if your answer is correct, so just count the number of electrons. We have 2 plus 2 equals 4 plus 4 equals 8. Okay? And then analyze the sequence. If it follows our pattern, 1s, 2s, and then we have 2p. Next one, for chlorine, it has an atomic number of 17, therefore it contains 17 electrons. It has an electronic configuration of 1s2, 2s2, 2p6, 3s2, and 3p5. Let us count. 2 plus 2 equals 4, plus 6 equals 10, plus 2 equals 12, and plus 5 equals 17. Again, just follow the pattern. We have 1s2, 2s2, 2p6, 3s2, and we have here 3p5. So that's all. These are the different references used for this presentation. And thank you for watching. Don't forget to click the subscribe button for more videos.